Okay, so I now want to look at a slightly different problem. It's going to be the t derivative of u is equal to the double x derivative of u plus pi squared over 4 times u. There's nothing really important about the pi squared over 4 except that it's just an easy number to work with, as you will see in just a minute. And we're going to have these two boundary conditions. This is an exercise in the notes. U of 0t is equal to 1. I think I'm going to keep these the same. U of 1t is equal to 2. And then u of x0, I'm going to keep this the same as well. U of x0 is going to be equal to x. Things are a little more generic in the notes, but I'm going to keep it like this. Okay, so we want to use, we have non-homogeneous boundary conditions. So now the difference here is that our equilibrium function is going to satisfy 0 is equal to ue double prime plus pi squared over 4 ue. And this gives general solution. The general solution is ue of x is going to be c1 cosine pi over 2x plus c2 sine pi over 2x. This is just solving a second order differential equation. Okay, now the initial conditions, the boundary conditions, if you plug in x is equal to 0, you get 1. Okay, now if you plug in x equals 0 over here, that term's just equal to 1, and the side term is equal to 0, so c1 is just equal to 1. And if you look at this and plug in x is equal to 1, this term is equal to 0, and that term is equal to 1, or it's just equal to c2. So in other words, c2 is equal to 2. Okay, so c2 is equal to 2. Now, as usual, or not as usual, but as we saw in the last video, v is going to be equal to u minus u epsilon, and so the problem that v satisfies is the t derivative of v is equal to the double x derivative of v plus pi squared over 4v. We've got homogeneous boundary conditions. V of 0t is equal to v of 1t, and they're both equal to 0. And now the initial condition, v of xt, is going to be equal to x minus ue of x. So I'm just going to write it as x minus ue of x. Okay. So now we want to think about solving v. Okay, so now how do we solve v? Well, it's a homogeneous equation. If we do separation of variables, the phi equation, or eigenfunction expansion, the equation for phi is going to be phi double prime plus pi squared over 4 phi equals minus lambda phi. And this is the same as phi double prime equals minus lambda plus pi squared over 4 phi. With the boundary conditions, phi of 0 equals phi of 1 equals 0. Now we've done this before. We've got phi double prime equals something times phi, and so we know that we're going to have, with this Dirichlet boundary conditions, and so we know we're going to have phi k of x is equal to sine of k pi x, and the corresponding eigenvalue is going to be lambda k. Well, this squared, the square root of this is equal to k pi, so lambda k then is going to be equal to k pi squared minus pi squared over 4. So what we're going to get then is v of xt is going to be the sum k equals 1 to infinity bk e to the minus, okay, it's going to be lambda k squared. So in this case, it will be k pi squared minus pi squared over 4 t times sine of k pi x. And what are the BKs? Well, the BKs is going to be 2 times the integral from 0 to 1 sine of k pi x times the boundary condition, or sorry, not the boundary condition, the initial condition, which in this case is x minus cosine pi over 2x minus 2 sine pi over 2x. And actually, instead of x, I like to use y as the variable of integration, so I'm going to have that there. I'm going to have a y here, and a y here, and a y here, dy. And so that's what bk is. So this is v of xt, and so u of xt is just going to be v of xt plus ue. So v of xt plus cosine pi over 2x plus 2 sine pi over 2x, and we get this right here. And so this is going to be the differential, or the solution to the differential equation. This is v, and this is ue right there, and this is the formula for pk. Okay, that was it. That's it for this video.